Sheng-Li Tan will use it. Thank you. So I have next slide is in the second part, so I will try to slow down the talk. The second part is about the invariance for the ODE of this type. So I try to generalize the Chern numbers for family of curves to some invariance of the ODEs. So Poincaré studied also this ODE. He introduced a Liu variable t. So within the Liu variable t, the two equations are equivalent. So usually we are interested in the real solution of the ODE. So we use this notation here. R is the real solution. This is the set. If the set a complex solution, we call this the foliation of the ODE. So actually, in 19th century, Dabo studied the ODE by using the algebraic geometry. For example, he extended the equation from R2 to CP2. This means from the real number field to complex number field. And he considered also the solution at the infinity. Here is the original equation. We can rewrite this as the differential form equals to 0. So the differential form, if you consider it in the plane, this is a global section of this bundle. So the cotangent bundle of P2. D is the degree of P and Q. In some cases, D may be less than this one. So projectively, the differential form can be written like this. This is a classical notation. And Dabo studied the number of singular points of this equation and the number of algebraic solutions of this equation. So what is the singular point of the ODE? The singular point means the common zero of P and Q. So for this singular point, we can define the multiplicity of the singular point. This is exactly the intersection number of the two polynomials at P. So for this ODE, we can consider the holomorphic solutions. So if C is a local holomorphic curve defined by a holomorphic function, C is a local integral curve if and only if you differentiate this equation, you get this. If you restrict it to C, you get this part. If this is true, we say that C is an integral curve, or C is a local solution of the ODE. So for a holomorphic foliation, F is just the solution, the set of solutions of this ODE. We can glue together the solutions. If it is a local curve, you can glue it if they are the same in the common set. So this means glue the solution. This is called the holomorphic foliation of the equation. Okay, if so here F is a family of holomorphic curves. We need to consider the solutions geometry. So in general, at any point in the plane, there exists at least one integral curve. So this means there is at least one solutions, holomorphic solutions near any point. So at a singular point, non-singular point, there are exactly only one integral curve, and this curve must be smooth at this point. So this is quite similar to the family of curves. So this, in some singular points, if there are infinitely many integral curves at P, then we call the point P as a diacritical singular point. So this corresponding to the base point of the family of curves. So this is why I introduced the notation of a singularity of a family of curves. So this is because of the same notation for ODEs. Yeah. You are right. Usually it is not algebraic. Yeah, you are right. Maybe there's no algebraic integral curve in some cases. So we use this notation f(a) to the power a means the subset of algebraic integral curves. So this may be an empty set. So this is the same picture. Here is the base point in the pencil of curves. Here we call this diacritical point. This is the notation of Poincaré. Here is a singular point of the integral curve, of one integral curve. So this is also a singular point. And a smooth point. Here is a smooth point. So in the family of curve case, a smooth point means a smooth point of a fiber of a curve in the family. It is not a base point. So we have the same notations. So sometimes the ODE is called algebraically integrable, or algebraic, if the set of holomorphic solutions are all algebraic curves. So the subset is equal to F. So this means any holomorphic solution, holomorphic integral curve, is a algebraic curve. So if the ODE is algebraic, this means there exists a holomorphic a rational function phi such that the ODE is equal to this one. So this part is equal to this one. So this means this ODE is obtained from the differentiation of this function. So in this case, we usually simply write this as the differential equation because it is obtained from the differentiation. So in this case, the foliation is equal to the subset. So the curve or algebraic curves in the set defined by this equation. So this is our family of curves defined by rational function. Okay, what is Dabou's result? In this paper, this is a very known paper. Dabou's result is he computed the number of singular points is equal to this one. And in this content, the multiplicity is considered. So if there are at least this number of algebraic solutions, it is a number of singular points. The multiple. Yeah, the same. Only depends on the degree of polynomial. Only depends on the degree. He considered also the number of algebraic solutions, algebraic curves in this set. If this number is at least this one, then the differential equation is also given by this kind of equation. Phi is a function, but it's not necessarily a rational function. So in this case, we call the ODE has a rational first first integral, but this first integral is not necessarily rational. So this is not necessarily a rational function. Meromorphic. Maybe complicated than meromorphic. Locally, it is defined by some holomorphic function to the power. The power is a irrational number, the power. Yeah. Okay. So this result is generalized. If the number of algebraic curves in this set is bigger than this one plus 1, then the ODE admits a rational first integral of phi. So in this case, phi is a rational function. This is yeah. Generic case, it is empty. Yeah, no algebraic solution. Panguri has 3 papers studied the ODE. Panguri has many papers about ODE, but these 3 papers is by using complex algebraic geometry. So I mentioned it here. So Panguri's idea is that he divided the algebraic ODE into 2 classes. The first class is the ODE algebraically integrable. So this means it is equivalent to the study of family of algebraic curves. This is a subfamily of the generic case. So the second class is algebraically non-integrable ODEs. His idea is to study family of curves to study algebraically integrable ODE, then try to generalize the result to the general case. This is the idea of Panguri. So the first problem Panguri introduced is it possible to decide if an ODE is algebraically integrable? So you try to find the algebraic solutions generically. And the general solution is algebraic. He divided this problem into 2 problems. The first problem is to try to find a height inequality for the solution, algebraic solutions. This is a height inequality for a rational function. This is the first integral of an ODE. So the height is just means the degree of the rational function. This is the height. What is the upper bound? The upper bound is a constant. Depends only on the ODE corresponding to the function. So we use the notation height inequality. The upper bound depends only on the differential equation. The second step is just algebraic calculation. Because if you know the upper bound of phi of the algebraic solution, you can check directly if the phi is a solution of the equation. Okay, this is the idea of Panguri. So what is H? It is easy to say that H is, you cannot use the degree of the degree of P and Q to bound this H. Because you can see in this example, this is the rational function. The degree can be arbitrarily large, but the differential equation is this. So the degree of the differential equation is 1. So we cannot use the degree of this one to bound this number. There are some examples to show that this number cannot be determined by the topological type of the singularities. So you cannot use the number of singularities and the multiplicities and so on to bound this H. So this is the meaning of the example of Lin-Slater. So this means it is very difficult to find such an inequality. Okay, Panguri's method, let's recall Panguri's method. We try to study the properties of families of curves, this this one, of genus G. This is a family of curves, so we have a corresponding fibration. Then we have the genus of the fibration. This is the genus of the family. So given by this one, by using fibration, this is the first step. The second step is to check if these properties can be recognized from the ODE, differential equation. So of course, this one determined by this equation. But Poincaré tried to find some properties which is only dependent on this differential equation. In the three papers, Poincaré first get a formula to the computation of the height. This is his height formula. If this is the curve in the family. So this is a divisor, so we have some multiplicities for each component. Here is the height. Here is the degree of the equation, ODE of this ODE. And here is the contribution of the multiple components in the family. His first formula. The second one is about some special ODE. Special means the ODE has maximum number of distinct singularities. So this means in opposite result, an ODE has always this number of singular points. Here, every singular point, the multiplicity is 1, so the total number is exactly this number. Then Poincaré got a formula to compute the genus by using the height and the degree D. Poincaré studied also this problem. For example, this is the main problem studied in this paper. This is a known paper, about 100 pages. This problem is, can we recognize the genus of the family from the ODE, from the differential equation? So this means, can you find a formula to compute this genus? The formula depends only on the data of this equation, differential equation. This is his problem. The second problem is similar to Poincaré's problem. But here, for a given genus, is it possible to decide if the equation admits a rational first integral phi of genus G? So here, the genus is considered. So Poincaré's problem is a special case of this Poincaré's problem. So for this problem, similar to Poincaré's problem, the essential part is to try to find an upper bound on the genus. If it has a algebraic solution, phi, then the problem is to try to find the upper bound on the genus. The upper bound depends only on the differential equation. So this is about a inequality on the genus. Okay, there are some counterexamples to show that the genus cannot be an invariant of the ODE. This means the genus cannot be computed from some information from the ODE. So we cannot find such a formula to compute it. So the upper bound cannot be determined by the topological types of the singularities of the equation, differential equation. This is the examples, latest example to show. The third one is G cannot be determined by the degree D of the rational function. Here we have a simple example. So we can consider this ODE. This ODE can be solved. So you can check which one is algebraic, which one is not. Actually, if the coefficient here is 2g plus 1, here is 2g, then this is algebraically integrable. The rational first integral is a family of curves of genus G. G is here. Actually, birationally, the family of curves is defined by this hyperelliptic equation. Because the ODE can be solved. You can check this result. So the degree is only 2 for the equation. And the singularity is very simple because there are some intersection point of lines. Here are 2 lines, here are 2 lines. So the singularity is very simple. Okay, how to generalize the ODE to alien compact complex surface? So we use differential form to describe the equation. So here, differential form means twisted holomorphic one form with isolated 0 points. So twisted means omega x tensor a line bound. This omega is a global section of this line rank 2 vector bound. So locally it is defined by this. So locally you can see it's an ODE we are interested in. Here, this line bound is called the normal bound of the equation, or the normal bound of the differential form. Here is a twisted differential form. So the 0 set of the differential form is exactly the singular point of the ODE, the common 0 of A and B. So it is the singular point of the ODE. So by the assumption, the dimension of this 0 set is 0. Consists of only a finite number of points. So we can introduce the canonical divisor of the ODE. Of this ODE. What's the canonical divisor? Canonical divisor is just the kx plus the normal bound. So this is called the canonical line bound of the ODE, or the canonical line bound of the differential form. Then we can define also the integral curves of this ODE, because the integral curve, the definition is local. So locally, this is just an ODE. So we can define globally integral curves of this global ODE. So we have also the foliation. The foliation means the holomorphic solutions of this one. So this holomorphic solution determines the ODE. ODE determines this one, and this one determines the ODE. So these 2 studies are the same. Okay, we can say that the ODE is algebraically integrable if f omega, the holomorphic solutions, is a family of algebraic curves. It is similar to the case in the plane. Okay, we have some algebraic geometry notations for this ODE. Okay, the next problem is how to construct an ODE from a vibration. So for a given vibration, we can define a twisted one form df. Then we get an ODE df. Yeah, Yeah, this omega.
Oh, yes,
This one. Exactly. Usually, I use different notations. Usually, one use the notation to mean the maximal invertible subsheaf of this one. The maximal invertible subsheaf. For this subsheaf, this is determined. So this sheaf determines by the global section. Yeah, it is maximal with isolated 0 points. So omega determines n omega. So in general, the differential form, this twisted differential form has one-dimensional zeros. This one. For example, the one-dimension zero for this differential form is just the discriminant divisor of the vibration coming from defined by this. So here, this omega has only isolated 0 point. So we can use this one to define the differential equation. Delta F is called the critical divisor of F. So S and ODE, this one is exactly this one. But the S section, they are different. But S and ODE, they are the same. Okay, for this vibration, the corresponding ODE, this one, the canonical divisor corresponding to the differential form, this differential form is just the relative canonical divisor. For this one, the corresponding canonical divisor is exactly the modular canonical divisor. So this means this one minus the critical divisor of the vibration. So the normal bundle is the normal bundle of the vibration defined by this. It's very easy to compute. Okay, for a pencil of algebraic curves on the surface S, this pencil induces a relatively minimal vibration, birationally, a vibration. So from this vibration, we can get a minimal normal crossing vibration. By blowing up the singular points of the fibers, you get this one. So the base is the same. We can define the genus of the vibration. This genus can be viewed as the genus of the pencil F. So we have also the Modular way rank for this family. This is independent of the blowing ups. So this is an invariant of the pencil. So we have, I mentioned we have relative chain numbers, but these chain numbers depend on the base. So they are not the invariants of the family. We have also the modular chain numbers, these three invariants. So they are good invariants for us. They are independent of the base curve. So it depends only on the smooth fibers. Okay, this is Serrano's result. This one is related to the ODEs. So the modular canonical divisor, the relative one minus the discriminant. I mentioned the theoretical decomposition of this modular canonical divisor. So the property of the theoretical decomposition relates the codec dimension of this divisor. So related to the property of the vibration. So VP is a big divisor. We know this exceptional set. Then we know the property of for this canonical divisor. If you consider the multiple canonical divisor of this one, You know they are base point free because of this. We know exactly the exception set of the divisor. Okay, in recent 10 years, someone generalized Serrano's result to the ODE case. For any ODE, we mentioned the canonical divisor of this ODE. So this is Kx plus the normal bundle, n omega. So this has a Zariski decomposition, P plus n. If this one has low Zariski decomposition, this means the differential equation comes from a rational fibration. The genus of the fibration is 0. So this is the easy case. The result is due to Mialka. So we consider only the case where K omega has a Zariski decomposition. Okay, we can define the Kodaira dimension, kappa. This is the Kodaira dimension of the equation, the ODE. We can also define the Kodaira dimension of P. This is called the numeric Kodaira dimension of the ODE. Use these Kodaira dimensions, we have some classification, some kind of classification, unrequest Kodaira type classification. So for example here, the Kodaira dimension is minus infinity. There are two cases. Rational foliation, this means a fibration. The fiber is genus 0. So it's P1 fibration. The second one is the Hilbert modular fibrations. I will explain. This is coming from the Hilbert modular surface. Here, the Kodaira dimension is 0. Only one case. The foliation induced by a vector field. This means our omega is exactly holomorphic one form, not twisted. It is exactly holomorphic one form. But here, this kind of foliation is a quotient of a foliation defined by a holomorphic one form. So just to say the foliation is induced by a vector fields. Okay, the Kodaira dimension 1 case, there are 4 classes. The Riccati foliation, the corresponding ODE is a Riccati equation. So Riccati equation, I will write down this later. The second one is turbulent foliation. This corresponding the turbulent equation, turbulent ODE. The last 2 cases corresponds in the algebraic geometry case. So this just the fibrations. So this for us these are easy. So for the general type case, we have low result. This is not my result. Someone due to many mathematicians. Okay, our purpose is to try to generalize our formula from family of curves to ODEs. So this, I mentioned the formula here. This is our formula. So we are trying to define these numbers for an ODE by using our new formulas. I will explain the formula here. Okay. How to define alpha f, beta f, mu f, the 3 parts. NF is just defined by this, so NF is very easy to compute. This is the self-intersection number. This part is easy to compute. Mu f is the number of is the total number of Miller numbers. I will explain these 4 parts. So we have to use the normal crossing model of the fibration. So by sequence of Boolean ups, we get a new fiber in the new surface by Boolean up the singular point of f then we get a normal crossing divisor, F bar. So from F bar, we can describe the invariance, the local invariance. So we denote by Mi the multiplicity of the reduced part of the curve, reduced curve at the center of the blowing up. So this means if you consider the blowing up, if you compute the multiplicity, here the exception curve is considered. So the strict transformation plus the exception curve, then you can compute the multiplicity. This is our Mi. Okay, with this Mi, we can define R of F. R of F is exactly defined by this number. So mu F is the total Miller numbers. This one. Actually, mu F can be computed from these numbers. We have also the formulas. Actually, these Mi are very nice invariant for the singularities. For example, if the multiplicity are over 2, this means F is a normal crossing divisor. And if Mi is less than or equal to 3 for any I, this means F at least at worst AD is singularities. So if Q is a singular point of the normal crossing model, locally defined by this equation, then we can define our beta Q. Beta Q is defined by this. So the inverse of this one is can be viewed as the height of a rational number, B over A. So this is some kind of height for rational numbers. Okay, we need some notation here. HGI branch, Hesburg-Young branch. This notation comes from the Hesburg-Young singularity. The Hesburg-Young singularity is resolved by a chain of rational curves. If in this singular fiber we can find such a chain of rational curves, this one is not in the chain. This means C is not P1 or C meets the other components in at least 3 points. So this means C is not in the chain, in the string of these rational curves. So this is a maximum chain of rational curves in the singular fiber. Remember here, F bar is a normal crossing divisor. So we have no other complicated singularities, only those as a singularity. Then we can define F, beta F minus and beta F plus. Beta F minus is the beta Q. I define the beta Q. If Q is a singular point here in the Hesburg-Young branch, then the contribution is denoted by beta F minus. Otherwise, the contribution is denoted by beta plus. So this is our local invariance. NF is G minus this one. So we explained the 4 terms, alpha F, mu F, beta F. In the formula for the chi-F, we introduce the notation dedicated number defined by this. P and Q are positive numbers, not necessarily coprime, because here is the quotient, the ratio. So here is the normal crossing model of the singular fiber F. So the multiplicity is here. Here K, this one with K components with these multiplicities. use this notation, we can get the formula for chi-f. Chi-f is just the nf bar, the nf of this one. This means genus minus the arithmetic genus of the reduced part, minus the contribution ni, nj is the multiplicity. Here, ci, cj is just the number of intersection points. So here is defined by this, that kind of number. So in the semi-stable reduction, we consider also this number, mf. Usually we use the base change at this singular fiber. The local ramification is this number. So using this base change, we can get a semi-stable reduction of the singular fiber. Okay, for a base change locally defined by this, the local base change only at the image of the singular fiber critical point of F. So we get the new fibration, the new fiber. The new fiber is denoted by F tier. It's the pullback fiber. So this is called the D model of F because of this the base change. If D is divided by MF, we know F tier is semi-stable. So D model is just the semi-stable model of F. If D is equal to -1 modulo MF, then D is called we call D is the dual model of F, and denoted by F star. So this is a generalization of Cordaire's notation F star. Okay, why the relative invariants are not a good invariance for us? We consider a base change. Base change, this is the older parameter, this is the new parameter. Base change is defined by this in general. So we get a new fibration. This is a global base change, not just a local base change. So for this base change, the relation of the relative invariance, this is the relation. We have only some inequalities. But for the modular invariance, at any base change of degree n, this is the relation of the modular invariance. So from these equations, we can say that the modular invariance is independent of the parameter t. Independent of this. If you replace this by another t, the relation depends only on n, so it is independent of the polynomial. This means independent of the base change, so independent of the parameter. So the modular invariants are independent of t, so it is a good invariance we wanted. Okay, in order to generalize the formula to the ODE case, we need some new formulas to compute the invariance, the modular invariance. The new formula depends only on the ODE, independent of the family. This is our next purpose. How to get the new formula? So we have to use the minimal normal crossing model of the fibration. So we can assume that this fibration is a minimal normal crossing fibration. So every singular fiber are normal crossing divisors. So if F has a singular point at P, locally defined by this, so the corresponding local differential equation is this. Then this is equivalent to this equation. Here the parameter is t. Then we can define the eigenvalue of this linear term. This is the linear term. So we have two eigenvalues. But these two eigenvalues are not invariants of the singular point. because you can this differential equation, this equation is not uniquely determined, x and y, the local equation. But this one, the eigenvalue of this one, this notation is a good invariant of the singular point. So we use lambda p to denote this. This is called the eigenvalue of the singular point of the fiber at the singular point p. So this is a negative rational number. We can also define this by this one. Both called the eigenvalue of the singular point. Okay, so we need to use this kind of topology. This one can be defined by the ODE, can be obtained by the ODE. So it is independent of the this equation. So we have to get in our new formula, every term should be dependent only on the differential equation. It is independent of the family of curves of the fibration. So for example, this number should be, we should define this by the eigenvalue of the singular point. This means if R is this rational number, then this number depends only on the rational number. If the rational number is fixed, this number is fixed. So this means our beta depends only on the rational number, depends only on the eigenvalue. Also, chi R, the dedicated number, depends only on the rational number R. So you can see if R is this term is R, this term is R, this is R minus, this is beta R. Okay, for a non-rational number, for any complex number, we can define chi by using this without this term, because we have GCD in this case. Then we can write our formulas. So here, the singular points of the singular fiber are divided into two classes, two types. One type is the singular point is a singular point of the branch, his HGI branch. The others are not on HGI branch. So for each singular point, we have only one invariant, the eigenvalue. So we can use the eigenvalue to describe our formula. So P belongs to HGI means these singular points. Okay, for fibration, we have the critical divisor of the fibration. We have the normal bundle of the fibration. We have the modular canonical divisor of the fibration. So using these divisors and the local eigenvalue, we get the new formula for the modular invariance. So this is simpler than our original formulas. So this is the, here, H is just the beta, our beta. I use a round notation. Here is just beta. In our case, lambda p is a negative rational number. So minus lambda p is a positive rational number. So this is the beta of this positive rational number. So the contribution of the singular points on the HGI branch. Delta F is the contribution of the other singular points. So lambda F can be computed by this. So chi is the dedicated number of the rational number. So this number or this formula are easier to compute because we know the divisors and we know the eigenvalues. Okay, how to get the formula for ODE? So the first step is to define the eigenvalue for a singular point of an ODE. So for example, the ODE, we can write ODE like this. So we can consider the linear part of the singular point. So we have a matrix M coming from this. The matrix has two eigenvalues. The two eigenvalues are not good invariant of the singular point, but the quotient is an invariant of the singular point. So we introduce the notation reduce the singular point. This corresponding to the normal crossing singular point. So one of the singular point of the ODE is reduced if and only if one of the following, if and only if these are true. The first one is one of the eigenvalues is non-zero. This means at least one eigenvalue is non-zero. We can define the eigenvalue of the singular point. For example, if the second one is not zero, we can define the eigenvalue of the singular point by using this formula. Here, it's not a positive rational number. So if it is a rational number, in the normal crossing case, this is a negative rational number. So if it is a positive rational number, you can, by using blowing up, you can get a new singular points. The new singular points maybe have a negative rational number as an eigenvalue. So this is the singular point of the ODE. This is the diacritical, non-diacritical singular point, smooth point. Okay, there is a similar resolution of the singularities for an ODE. This is due to Seidenberg. So after a finite number of blowing ups, the pullback equation, that means at worst reduce the singularities. So in the family of curves, the pullback vibration is a normal crossing vibration. The result is the same. Suppose the ODE is algebraically integrable. This means it is induced by a family of curves given by rational first integral. If in this case, if the ODE is reduced, then the family of curves must be a vibration. So it is reduced if and only if the corresponding vibration is a normal crossing vibration. So reduced model is the normal crossing model of the family. So from this, we can say that the two resolutions are the same. So one resolution is for family of curves. The final vibration is a normal crossing vibration. For ODEs, the final ODE is a ODE with reduced singularities. So our purpose is to define the Chern numbers of this ODE. So we have to introduce the similar notations, lambda f, the normal bundle, and modular canonical bundle, and these two bundles. Actually, we have defined these 9 bundles. If omega is an ODE, this is an ODE. We have the foliation and the subset, algebraic solutions subset. So we have the Seidenberg's resolution of the singularities, the reduced model. We can assume that this differential equation is a reduced differential equation. This means all the singularities are reduced. So because this is a set of algebraic curves, so we can consider also the Hessenberg-Young branch in this subset. In the vibration case, we consider the Hessenberg-Young branch in the singular fiber, in the fibers. Actually, integral curve, the corresponding notation is the fiber component. So we can define the Hessenberg-Young branch in this subset. If we the algebraic integral curve, the chain of rational curves. We call this the Hilbert-Young branch of the foliation. So if P is a singular point on this Hilbert-Young branch, the lambda P is a negative rational number. This is similar to the vibration case. Then we can define the Chern numbers of the ODE. So this is quite similar to our formulas, the new formulas. So this is the relative, the Chern numbers of the ODE. This is the local contribution of the eigenvalues corresponding to the singular point on HGI branch. And the C2 only contributions of the other singularities. The singularities, the eigenvalue must be a rational number. Because they are reduced, the rational number means a negative rational number. So C2 depends only on the singularities, not on the Hilbert-Young branch. So chi-F, use this formula to define chi-F. Actually, we only need these two because we have Noether's equality. So this one is more complicated. We only need this one. Okay. We want to know the properties of these Chern numbers. So we call this the Chern numbers of the ODE. The first is Noether's equality, like this. So we only need this one and this. Sorry, here should be omega. They are positive numbers, positive rational numbers. This is similar to the modular Chern numbers. We have inequalities like this. This is because of this one and the non-negativity of C2. Here should be omega. So this is if this equation, if the equation omega equals 0 is algebraic, this means the foliation is induced by a rational function or a family of curves. So we have the genus. For this kind of equation, we can define the genus. For general differential equation, we have low genus. Then we have this slope inequality. This is a translation of the slope inequality for vibrations. Okay, the Chern numbers are birational invariants. So this means the Chern numbers is independent of the blowing ups. So the modularity means if the differential equation is algebraically integrable, this means because omega is a reduced differential equation, if it is algebraic, then the corresponding family of curves is a vibration. In this case, we have two invariants. This one is defined by the ODE. This one is defined by the vibration. In this case, they are the same because we generalize the formula for F, so they are the same. So rationality means if the canonical divisor of the ODE is not pseudo-effective, this is equivalent to the solution is a rational vibration. Because this is the omega is reduced, so if it is algebraic, it corresponding to a vibration. So the vibration is a rational vibration, means the fibers are rational curves. Okay, the Zariski decomposition I mentioned before. Suppose omega is not in this case, in Miyaka's case, then K omega has a Zariski decomposition. So P is the positive part, N is the negative part. So in this case, our Chern numbers, first Chern number is exactly the self-intersection number of P. So from this, we can say that C1 squared is non-negative. C2 is non-negative from the definition. So Chi-F is also non-negative. C1 squared is positive if and only if the differential equation is of general type. This means the canonical divisor, the Godai dimension is 2. Okay, we can use some slope inequality for fibrations to get some solution to Poincaré's problem or Pan-Navis problem. For example, for some special ODE satisfy this inequality, we consider this special ODE. If this ODE is algebraically integrable, and the G is the genus of the corresponding fibration, then G is bounded by the Chern numbers. So this is a problem, is a solution of, to the problem of Pan-Navis. More exactly, if A is a positive integer, and we write this exactly by this, then we can get then we know that A is the upper bound of the genus of the corresponding fibration. For example, if A is 1, the inequality here is C1 squared is less than 2 chi. If A is 2, here is 8 over 3. Okay, Xiao has some examples to show that the condition here, we cannot drop this condition. Xiao constructed some fibrations. The corresponding ODE satisfy this equality. The genus can be arbitrarily large. So we cannot bound the genus for ODEs with this equation. For example, if we take A to be 1, we use this condition to control the ODE. If the ODE satisfy these two inequalities, then we can say that this equation is not algebraically integrable. Why? Because we suppose this omega is algebraically integrable, and this corresponding to a fibration. Because these are birational invariants, you can assume the equation is reduced, the singularity is reduced. So this corresponding to a fibration of genus G. So applying our theorem I mentioned to the case A, so this A here is 2, so satisfy our condition in this inequality. A is 1, the inequality is here is the coefficient is 2. So this means we can bound the genus G. G is less than or equal to A is 1. But for genus 0 fibration and genus 1 fibration, the modular invariants are always 0, the first modular invariants. So this is a contradiction to this inequality. Okay, in order to know the properties of the modular invariants of the ODE, we needed to compute some examples to get some information about these invariants. Here is an example. We constructed some family of curves of genus G satisfy this. G can be arbitrarily large. but the Chern numbers of the corresponding ODE is not big. My former student Liu obtained the optimal neural bound for the genus 2 case for the modular invariance. If this family is not isotrivial, this means these two numbers are positive. So this is the optimal neural bound for genus 2 fibrations. So maybe our invariance can be used to classify ODEs. In the birational case, we only know the ODE can be classified into 7 classes, but we have to use to get the biregular classification of the ODEs. Without this is the birational classification. So we need a biregular classification, similar to the surface case. So for the biregular classification, maybe we needed the Chern numbers. For example, for the non-general type case, this Chern number is always 0. So we have only C2 for those equations. So we computed the Chern numbers here. This is the birational classification. So for the question mark, we don't know the lower bound for these equations here, for classes. So what is the here but the modular foliation? Foliation induced by vector fields, recursive foliation, turbulent foliation. So we can use the language of foliation. We can also use the language of ODE. They are the same because ODE determines the foliation. And the foliation determines the ODE. So the two notations are the same, ODE and the foliation. Okay, I will explain the special notation, special foliations. So a rational foliation is just a fibration. The genus of the fiber is 0, is P1 fibration. So this is the this case. This is due to Mialka. What is here but the modular foliation? This means the foliation is induced by a factor h of a Hilbert modular surface. So Hilbert modular surface is this cross h modular sum group. And one factor induces a family of holomorphic curves on h cross h. In the quotient, it gets a family of local holomorphic curves on the Hilbert modular surface. So every factor induces a family of foliations. So the family of foliations corresponding to some ODE. So the Hilbert modular foliation is just one induced by one factor. So on this surface, we have two foliations. So this is corresponding to this class. What is the Riccati equation or Riccati foliation? Riccati equation is an equation of the following type on a ruled surface. This means x maybe y is the coordinate of the fiber of a ruled surface. The right-hand side is just a quadratic polynomial of y. So this is called the Riccati equation. So an equation is induced by a vector field, or the foliation is induced by a vector field, means omega is a holomorphic one form, exactly one form, not twisted one form. This is the class corresponding to here. Modular quotient by group action. The last one, turbulent foliations. This is concept comes from the corresponding ODE. The ODE is called turbulent equation, ODE, turbulent ODE. The corresponding foliation is turbulent. So this is the birational classification. So our next purpose is to do the biregular classification, holomorphic classification. So for this classification, for example, here, maybe there are some many classes. We have to use the Chern numbers to classify these foliations or the ODEs. Okay, I stop here. Thank you.
Any questions? Excuse me. You use algebraic geometry to study differential equations. Are there applications in the reverse direction?
Yeah. My students are trying to compute some examples to see the relationship between the Chern numbers and some interesting things for ODEs. But we just finished this, so we have no more applications. So I hope the formula, the new formula is easy for you. Okay, thank you very much.